Hello, I'm Cheng, a junior from Harvard Wesley School in Studio City. In Parkinson's disease patients, alpha-synuclein monomers abnormally aggregate into fibers, driving neuronal death. Previously designed structure-based D-peptide inhibitors of alpha-synuclein fiber caused death of C. elegans, a model of Parkinson's disease, and this raised my research question. Can we modify these inhibitors to maintain their ability to prevent alpha-synuclein aggregation while avoiding the death of C. elegans? The best performing candidates all have poor water solubility. Inspired by other studies, I hypothesized that the death of C. elegans is caused by the low solubility and consequent poor biocompatibility of the D-peptide inhibitors. Based on previous data, I identified MWVY as a promising core segment. To enhance solubility, I choose to add charged residues to the ends of the core segment because they can form ion dipole intermolecular interactions with water molecules. To enable later testing, the first step is to validate that the inhibitor binds to the alpha-synuclein fiber. Using Rosetta's protein-protein docking protocol, I calculated binding energy between alpha-synuclein fibers and my designed D-peptide inhibitors, with lower or more negative energy scores indicating stronger binding. After inputting the structures and running calculations, results show that DMWVYK has the strongest binding affinity, followed by KKMWVY. Then, I conducted a turbidity test using inhibitors at concentrations 1, 2, 3, 4, and 5 millimoles. Higher turbidity signifies increased precipitate formation, which suggests lower solubility. 3 experiments were designed to examine how residue number, charge, and position affect solubility. The key findings here are that first, adding 2 charged residues improves solubility more than adding 1. Second, positively charged residues enhance solubility more than negatively charged ones. Third, residues of different charges have distinct positional preferences for enhancing solubility, with positive residues positioned at C-terminal of the core segment exhibiting greater solubility compared to those placed at N-terminal, while negative residues show the opposite trend. Lastly, I conducted a C. elegans experiment to test alpha-synuclein aggregation inhibition in vivo. First, I bleached C. elegans to remove adults, leaving only embryos to ensure synchronization at uniform developmental stages. I then let the eggs hatch and grow for 3 days. After that, I treated them with different inhibitors. I then transferred them to an NGM plate. After that, I fixed the worms onto a microscopic slide and used fluorescence microscopy to visualize alpha-synuclein aggregation via FRET. Here are the pictures I took. In front of each, the inhibitor it is treated is labeled. The graph can show that DMWVYK and KKMWVY significantly reduced alpha-synuclein aggregation seeding, with p-values of 0.011 and 0.0032. This is because of their strong binding, as evidenced by the Rosetta energy calculation, and good solubility, as evidenced in the turbidity test. The major conclusion I draw from this project is that KKMWVY best inhibits the formation of alpha-synuclein aggregates based on the comprehensive results of previous tests. The refined peptides not only allow C. elegans to survive, but also inhibit alpha-synuclein aggregates formation. From here, our research question is solved. These structure-based D-peptide inhibitors with optimized solubility, specificity, and bioavailability represent promising therapeutic leads for Parkinson's disease and other related alpha-synucleinopathies.